Thank you so much for inviting me. I'm very impressed by this eager audience. I'll try to do you justice. So that's our logo, and I'm told that occasionally bobcats can be spotted on our campus. Just the day before classes started, I had a visitor. And the visitor made me feel right at home because he knew something about me. So I show the visitor, and I also show our first chancellor. Where's the laser pointer? You have that? Laser pointer. Okay, thank you. So Carol, not working. It's not working. Yes, it is. Carol Tomlinson-Kesey was the founding chancellor. She was an absolutely wonderful chancellor, and she felt her job was done last May, and now we have a new chancellor coming, the Dean of Engineering, Steve Kang from Santa Cruz. So things are changing. Okay. So our program has three aspects: photovoltaic, thermal, and lighting. So I like to think of these areas as on the supply side of energy. I mean, you can. So energy has a study of energy appropriate to universities has two components. You can study the demand side, and you can try to figure out how much do you need, how much is left, how do you conserve, and that's very important. But you can also innovate and produce methods of actually producing energy, and that's what we're about. We're about the supply side of energy, and I'm pretty sure we're the only campus that does that in any serious way. But I can be contradicted on that. Okay, so in order for you to, it's not so easy to see. Can the lights go down?
Let me turn on the lights.
In order for you to have some idea of how we do our energy supply, I need to introduce you to nonimaging optics. I cannot assume that you've even heard of this subject. So what follows is a bit of a lesson. Okay, so what follows is serious, and it's a bit of a lesson on what is non-imaging optics. Because without non-imaging optics, we couldn't do the solar energy work that we do, and neither could anybody else. So, all right. Probably there are two important aspects to non-imaging optics. One is what can be done, and two is how do you do it. Okay, what can be done, and this is worth paying some attention to. We don't teach this in our classes. Our students don't learn this. So I suspect not too many people in this room, probably zero, would know the sine law of concentration. But let me show it to you. Let me show it to you in a very, very simple physical way without a lot of math. Okay. So imagine a spherical energy source like the sun, and the power per unit area, the flux, falls off like the distance to the sun squared. That requires no math because the same power goes through a sphere of 4 pi r squared, and therefore the flux, which is power per unit area, falls off like 1 over r squared. Now, if you accept the proposition, which I'm sure you do at this campus, that nothing you can do on the Earth can more than reproduce the solar surface flux. If you could actually do better, you could have a perpetual motion machine. So I don't think I need to spend too much time on that. So therefore, the most you can do is boost the solar flux on Earth by the ratio of big R to little r. Right? And of course, this is a nice right triangle, so that's 1 over sine squared theta. So this immediately generalizes. throw away the sun, throw away the earth, just imagine a beam of light with some angle theta. You can concentrate that beam by 1 over sine squared theta. And in case there's a index of refraction, there's an index of refraction here. And another way of, so n squared. Another way of saying this is that given a concentration ratio for your apparatus, the angle, the sine of the angle is n over root c. Okay? Yes, I'll come back to that. That's an important relationship. For small angles, the angle itself in radians is n over root c. So I'm interruptible, and I would hate to go on if this isn't crystal clear.
What's n?
What? Index of refraction. Index of refraction at your apparatus. That's a good question. So does anybody not see this? This is the kind of thing you can do on the back of an envelope and tell your friends about it, colleagues. Right? Okay? Good. All right. Okay, so that's the what can you do. That's nature. That's what nature allows. Now, how do you do it? How do you do it? Okay. So I think the naive approach has always been to take some nice focusing device. Here I've used Mount Palomar as an example. And it's a good thing that the words are spelled out here because I have a really, really bad cold and I can't talk very well. So you think a telescope would be a great concentrator. Okay. And let's just see if that's the case. Let's see if the telescope mirror can give us 1 over sine squared theta. Well, if you do a simple analysis, again, this is a type of analysis you can do in the back of an envelope. Physicists love backs of envelopes, right? Napkins. You find that you're off by a factor of 4. Okay? So what you thought was a good concentrator is off by a factor of 4. Okay? That's worth knowing. Factors of 4 are huge. Okay? So that's worth knowing. This is just the napkin type of so I urge you to try it for yourself. Here's a telescope mirror, a beam of light, spreads by this much, take the ratio, and you'll find a 4 downstairs. Okay, so this is not even high school, probably junior high school geometry, right? Okay. And if you have a cylindrical absorber, then you're off by a factor of pi. So whether it's pi, whether it's 4, these are significant factors. If you have a technology which can have a pi or 4 advantage, that's significant. Okay? And that's what non-imaging optics brings to the subject. So it was the desire to close the gap between what classical optical systems could do and what nature allows you to do that non-imaging optics was developed. So it was developed to close this gap. So clearly, non-imaging optics has to have a different set of algorithms. It can't look like parabolas and lenses, right? So one way to explain non-imaging optics is to say that the optical path length along strings, and I'll tell you what strings are a little bit later, are constant. So that's one. This is one way to describe the algorithm. And in the physics department, this resonates because strings are popular with some theorists. But here, I don't see much reception to strings. Okay. Maybe you don't care. All right. And another way to get at this is to double the number of dimensions. And that's very powerful. So phase space, that is to say both coordinates and momenta, is a very powerful way of looking at these problems. In fact, I would say it's the only way to look at them. So again, what's phase space? Well, I'll sort of explain it a little bit. But phase space, you double the number of dimensions, not only the position of a light ray, but also its momentum. And in geometrical optics, the momentum is just the direction times the index of refraction. Okay. Do I see signs of recognition, or is this all? Questions are really welcomed. Otherwise, I don't know that I'm communicating. All right. Okay. So, by going to phase space, we can actually make progress. One reason that phase space is so useful is it has lovely properties, like the volume is conserved, like an incompressible fluid, okay? And it also gives us an algorithm for solving the problem. Okay, so here's the algorithm. And so this is worth, okay. So if we just get this through and nothing else, I think I'll have done my job this morning, this afternoon, okay. So this is non-imaging optics in one slide, okay. All right, so let's suppose I'm making an image of an object. I'm representing the object, just a one-dimensional object, and it's got some points here. And these points are imaged to these points, so it's a mapping. So imaging is a mapping, okay? And mathematicians treat it that way, and fine. But if you think of it in the phase space representation, each point is all directions. So each point has over all possible directions. So if we now plot not just positions and not just x, but also the direction cosine with respect to x, which turns out to be the x component of momentum. So if you plot the x component of momentum and the position, each point here is a whole vertical line. Okay? And the job of an imaging device is to map line to line. So in that sense, it's a two-dimensional problem, and usually cannot be solved exactly. Okay, so usually you can't exactly solve imaging problems, and people have various approximations. So you do pretty well, but it's very difficult to have perfect imaging systems. Okay, so now if you turn around and say, so think of it another way. Think of the perimeter of this phase space volume, which has all the rays, all the energy, all the points, all the rays. Okay, so it's the perimeter. If I could map the perimeter to here, then the area stays the same. My volume doesn't change in the phase space transformation, and everything inside stays inside. And therefore, I've done my job of transferring energy in a completely correct way. And I've met the sine law, because I think you can almost see in your head, just mentally, you can see that this perimeter can be squeezed in distance, and then the L can go to 1. So that gives you the ratio of the two spatial dimensions equal to sine theta. Okay, so you can almost, I think you can almost see that. So that's the idea of non-imaging optics, to map the perimeter of the phase space region. That perimeter is one lower dimension, and you can actually solve that problem. You can solve that problem, as we say in physics or math, in closed form. It's nice to be able to solve problems just like that. No approximation, no numerics, just solve it. So that's non-imaging optics. Questions? I should have prompted. Oh, good. Thank you.
Going from L to L prime in your second line of
Yeah.
features,
Yeah.
is that actually dispersing light waves?
No. The L is direct. L is the direction cosine in the x direction. Okay. So you have x and cosine theta x. Okay. But you're mapping. You're going from here to here. So the prime is you're going from here to here. Prime means the image, if you like. Unprime means the object, if you like. Even though you're not. Where's the light? I lost the light.
I guess what I'm trying to ask, is that an example of diffusing versus concentrating?
No. This is an example of energy of maximal efficiency energy transport. That's what this is. Where you don't care what happens to the information inside. You just don't care. You only care about the power. Well, maybe this will become more clear as I give examples. So let's wait. I was afraid of it. Start coughing. So I think I've already told you that. I've already told you that, so I'll go on. So again, the magic of phase space. The volume doesn't change. The problem is solved by mapping the boundary, and that's a lower dimensional problem, which you can solve and you can just solve in closed form. Okay? So that's what the subject is about. You can solve that one. Whereas you can't solve the two-dimensional problem. Okay. Another way to think of this is if the volume in phase space is represented by a plastic bottle, and you fill it with water, which is incompressible, and fill it with alphabet blocks, which spell out CITRIS, for example, then if you want to move that bottle across the room, you have to be very, very careful, right? Because otherwise they'll scramble. But if you just want to move that energy, you'll just toss it to the person there. It doesn't matter. Okay. Okay. So I'm about to start something new, and therefore I want to make sure that nobody has any lingering questions. Yes, sir.
A point becomes a line because
all directions. Yes, because the point becomes a line because the point has all directions. All directions.
And therefore, the reflections are all of the individual angles of incident and refraction.
Well, we haven't said anything about how we do it. We haven't said reflection. We haven't said refraction. We simply made a little diagram where each point, as you correctly said, each point becomes a vertical line, and you need to move the lines over. But if you're non-imaging, you could care less. The lines can all just blur together. It doesn't matter. But that was a good question. All right, I'll go on. So let's go back to the string. The string method is a way to map the boundary of the phase space. And I'm throwing words like Fermat in because you'll see in a minute that this kind of is reminiscent of imaging where the optical path length is the same, but it's different. So you can make the following bold statement, which is actually correct, that all of imaging optics, everything that leads to all the sophisticated lenses that we use on our cameras, et cetera, the principle was invented by a 17th century French jurist, Pierre Fermat. Okay? I guess you know that, right? So the principle is that the path length from object to image is the same for all paths. So that's a very powerful principle, and look at the date, 1601, okay? So 17th century. So there are many ways you can see that. You can marvel at it, how somebody could have such a powerful insight. Or you could say, well, here we are in 2000 something time, maybe it's time for something different. Okay? So I need to show you what strings are. So the way I'm going to show you is by actually doing it for you. So this is a different way of showing something, which I personally find very satisfying. Instead of some boring proof, which you can always wonder, oh, maybe I believe, maybe I don't. You do it, okay? You do it, and there it is in front of you, and then this disbelief should vanish. Okay. So if you want the sine law of concentration, and this is not very weak, I can barely see it. Are there any other laser pointers? At this point, a laser pointer would be really useful. Where's our audiovisual department? Yeah, this is becoming invisible.
I'll have to go to the one.
Okay, all right. How about a long stick? Because I really need a pointer. Okay, it's back. It's recovered. All right, all right, all right. So if you want to go from entrance to exit in the ratio of the sine of the angle, so the area goes like sine squared, you are instructed to do the following. You take a object that I always think of as a curtain rod and attach a string to it, okay? And the other end of so one end of the string slides on the curtain rod. The other end of the string is tied to the exit aperture. And you now just move the string along this profile. Okay? Just move the string. Keep it same length. It's always the same length. So when you start, you've got this length plus this length. That's the length of the string. Okay? When you finish, down here, it's this length plus that length. So since the cross lengths are the same, they cancel, this length is equal to this length. It's sort of almost silly, right? But what is this length? This length, right triangle, is the aperture times the sine of the angle. So you're finished. So you have done it. You have actually performed a sine theta concentration of light. You never asked about imaging because this had nothing to do with imaging. But you've done it. So this is proof by showing. Okay? I'm happy to pause for questions. Here's how you do it. Okay, so this is all you have to do. All you need is a little bit of string. That's it. And if you don't want to use string, you can program this, right? Okay. So you can do more exotic receivers. More exotic receivers. Let's do a cylinder. Okay. So you might wonder, oh, what to do now? Well, you wrap the string around the cylinder. So now this length, when you get all done, becomes a circumference, 2 pi a, which is just what you want for a concentrator to a cylinder, because the surface of the cylinder in cross-section is 2 pi a. So it's just what you want. Thermodynamically, it's just the result you want. It's back. It's sort of back. It's sort of back. So thank you. So do you believe this? I don't know. Seems to work out. So it does work out. Try it. It gives you the right relationships. Okay. And this, of course, becomes a reflector. And we'll be using this in a few minutes for applications. This is after all, a solar energy talk. Okay. All right. So I always like to show recent success stories with non-imaging optics. This is a few years old. It's the Sudbury Neutrino Observatory, which made the spectacular discovery that neutrinos have a little bit of mass, which is not understood, very, very small, but that's a spectacular discovery. Okay? Another success story is this year's physics prize, the Kobe radiometer. Now, I gave this talk 3 times at Stanford, and twice in that audience we had one of the discoverers of this, of Penzias and Wilson. So it was an opportunity for me to recognize Arno Penzias and to say a little bit about the cosmic black body radiation. Okay? Good. Now, down to very practical things. So we kind of left the ethereal overview, and now we're down to practical things. So if you came here wanting to know how can I get a more efficient photovoltaic system or a more cost-effective thermal system, that's the next part of the talk. Okay? All right. So as I said, at UC Merced, I decided some time ago, looked around what was going on in the other campuses, and I saw beautiful work going on the demand side. It was studying energy use, studying how you can use less energy conservation, more efficient lighting. These are all hallmarks of the research that's gone on at Berkeley. But I didn't see anybody working on better ways of producing the energy. So I thought this would be a good subject to work on. Okay? So at some point, at some point, you can conserve and conserve. It's a good thing to do. But at some point, we need to replace fossil fuels. Right? And the sooner the better. I'm sure you all agree with that. So, in photovoltaics, there's sort of a magic number of $1 per watt. And it's not there today. It's almost, well, it's maybe halfway to 10 per watt, maybe 4 or 5 per watt. So even at $1 per watt, it's not quite competitive with a coal plant, but it's still interesting. So what we go after in photovoltaics is something which can be inexpensive, reduce materials cost, and have efficiency, and have acceptance angle. Acceptance angle turns out to be very important. And I've already told you what the acceptance angle is. It's 1 over root C, or n over root C. Okay. This is an interesting graph. And it's busy, but all I ask you to do is to look at this thing over here, this part over here. Efficiencies, year. So there is one technology which is improving very rapidly, okay? And it's the multi-junction cell. Maybe I get a poll here. How many have not heard of the multi-junction cell? Have not? No, okay, a lot of you have not, okay. Well, so I'll tell you what it is, okay. So this is obviously, if you have a 40% conversion of solar to electricity, that's very good. I mean, if you think of what is a power plant? What is a coal power plant? I think it's somewhere maybe in the 40s, 50, well, around 50. It's not much more. So this is starting to challenge fossil fuel power plants. Okay, so this is very, very good, and we have keyed our work to this, what I consider a truly marvelous development in solar cells. Okay, so here's how these triple junction cells work. There are 3 cells in series, so it's like 3 batteries. So each junction is a battery, and the junction voltages add up. The currents are the same. I think I can show that. And each junction is a different color. So there's a blue junction and a green and a red. So this is sort of like going from a monochrome LED to an RGB, right? So it's covering the solar spectrum better, and therefore, in principle, you could be up in the 80s. In principle, okay. If you had enough of these junctions, you could. Okay. So how does this work? You see, the current has to be the same, conservation of current, same in all 3 junctions. Think of each as a battery in series. The current is the same. The voltage adds up. So for those of you who work with solar cells, the voltage, instead of being about half a volt, is more like 2.5 volts. Okay? So does everyone see how these multi-junction cells work? I think it's a very important development in materials research. And the way we, let's see, now I wanted to, let me just quickly peek. Okay, so I wanted to, okay. So there's always a but, and the but in this case is that the cells are very expensive. Okay? Oh, nowhere near practical for the way that we put solar cells on roofs. Okay, if they were, well, problem solved. But these cells are very expensive. They're made small, so they require concentration. Okay? And in fact, they work better under concentration. The voltage is better. Voltage is larger. So these cells require concentration, and that's what we set out to. That's what we set out to. So if you look at what the world is doing, this is something odd in Australia. It's huge. The trend is towards smaller, and this is something less huge, still big, not as big, and the evolution we've gone through is from this sort of thing to tiny micro concentrators. So that's kind of the evolution of our work. And we work with we don't make cells. We work with industrial partners. One is Soul Focus, which is a park in Palo Alto. Another is Spectral Lab Silmar, which makes the cells. So we started with something very simple, that, and then graduated to something which was miniature. Okay, this is now like an inch. Okay, so miniature type thing. So these are under development. I should say that this one is kind of in prototype testing, and this one is under development. So this one is being developed right now. Okay, and so its characteristics are it has the right concentration. This should be a theta, and it looks good. It's important. Very compact and all that. Okay. So as I said, the first version is pretty much being tried out, and here's like a 2.5 kilowatt array. Each little thing here is one of those units I showed. So this is about 2.5 kilowatts, and that's over at the Palo Alto Research Center. Okay. And this is really just the beginnings of the tiny, tiny concentrator, just the beginnings of it. So we try to make like a university and try to improve things. So one way to improve things is to make it turns out that you want uniform illumination on the cell, and the way you can do that is to put little Kohler elements here, just bumps. You can kind of intuitively see if you do that, you get a more uniform illumination. That's a technicality. I'm not going to dwell on that. That's what it looks like. So we're putting together an array like this now, about 60 of these units. It's fun to put stuff together. The students love it. I love it too. And actually, not study things, not just study things, not just have pictures and artist things, but really real things. I think that's very important. You can imagine these on rooftops, but that's to be seen. It's to be seen. Okay. So to give you some sense of, so my next direction in this multi-junction stuff is kind of inspired by an experiment I did in my former institution with just one student. It was one of the easiest experiments I ever did. The goal of the experiment was to have a larger solar flux in our experiment, and our experiment now was on the roof of a building in Chicago. Okay? Have a larger flux in our experiment than you would have at the surface of the sun. And the way you can do that is the index of refraction. Okay? Index of refraction. So this was...
Roland, there is a question.
Yes, sir.
How are the three cells mounted with respect to each other?
It's layers. They're very, very thin layers. They're about 20 layers. So they're not three cells. It's one cell. Where is it? It's not that. It's okay. I don't have a picture. Okay, I don't have a picture of a cell. It's extremely thin layers. It looks like one cell. Okay, just layers of material, right?
Okay, so the photons go through one cell.
They go through. No, it's one cell. It's three layers.
Through one layer.
One layer.
And then the next.
Right,
layer.
right. So the layers are this one, which likes the blue, and this one, which likes the in the middle, and germanium, which likes the red. But if you look at it, it's one cell.
Okay.
Yes, sir.
So why do you want to use the expensive one why can't you just use the other one? You're trying to optimize your power per unit cost, really, right?
Right. The idea is that if you concentrate enough, the cell cost goes away. You replace cell cost by common materials like glass and stuff. That's the idea. If that works out, we'll see. So the idea is to try to take advantage of this 40%, which is extraordinary. But you can't do it without concentration.
This technology requires a dual axis tracker, right? That you
Yes,
constantly-
it does. Yes, it does. Yep. Okay, so here's the experiment. I borrowed a telescope mirror which was very weak. This is almost it's almost flat, right? So by itself, it only gave 1600 something, which is rather small considering that the limit is 44,000. But by adding a secondary out of a high index material, which is sapphire, this 40 centimeters went into a millimeter. And that was the experiment. So if you do a quick estimate of 40 into a millimeter and put in some reasonable losses, it'll be plausible that we got about 84,000 suns. So this is how we measured it. Measuring it turned out to be the only challenge, how to measure it. Here's the calorimetric technique to measure it. Basically, you put solar flux in, you compare it to electrical resistance heating, the ratio gives you the power. You can measure electrical resistance power extremely well because you can measure voltage and current extremely well. So here's the student and the setup and experiment. And we actually got 15% more than the surface of the sun, which was an interesting conversation point. But doesn't violate anything because of the n squared. Okay, so now we're almost ready to switch to thermal. So now, if you look at what's going on in the world, you can see that these folks haven't heard this talk. So this stands for various companies, okay? And here are their concentration ratios. And here are their efficiencies. Well, they're not so bad. But here are their angles, usually less than 1 degree, okay? So if you do this n over root c calculation, for 500 you should have 3 degrees. And for 150 you should have 5 degrees. Okay? So we decided that the rest of the world doesn't know what it's doing, and we're going to do it this way. Always a dangerous thing to do, but okay. So just to rub it into all those other people, I plagiarized from Benny Goodman. It doesn't have that swing. Okay. So here's the kind of design we're working on now, quite assiduously. I'm really quite excited about it, actually. Almost overcomes my cold. Simple, low materials, high efficiency, high angle, blah, 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 all that stuff. Okay, so this is a straw man design. This is just to throw out one possible way. There are a myriad ways of doing this if you use non-imaging optics. One possible way, really, really simple. So you know what a straw man means, right? And that's the Burning Man, okay? Burning Man Festival. So here's the straw man design that we've inflicted on people, where the angle will be 3 degrees or 5 degrees. And what it looks like is a very, very simple lens. Remember, the beauty of a non-imaging object, you can take a crummy optical element and make it work exactly as sine squared theta. So you can take a crummy Fresnel lens, and these are available bonded to glass, so they stand the elements. Okay, so they withstand long exposure to the elements. A non-imaging secondary solar cell heat sink, done. Okay, so this is causing some consternation, I think, right now in the community. So I'm about to switch over. Yes?
How do you choose what acceptance angle you use?
Oh, there's a formula for it. The formula is n over root c, right? So the formula is 1.5 over root 500, which is about 3 degrees. So you don't choose it, it comes out. What you do choose is concentration. The concentration is driven by economics. These cells are expensive, and you need something like 400 to 600 to make them affordable. I saw another hand. Yeah. Yes. Go ahead.
Does that presume that the rays come in parallel? I mean, there's a minimum acceptance angle that you can get with the sun, right? Because the sun has a significant cross section.
Oh, wait, the sun's a quarter of a degree.
What's that?
The sun's a quarter of a degree. Yeah. There's another question.
So you, on a
Yeah.
And you're using these heat sinks, right? So is there any work to put a thermoelectric or Stirling engine to actually use that heat for a useful gradient?
Well, actually, there's some work with Stirling on technology I'll show shortly, but on the other, no, not that I know. Anybody else? Yes, sir.
What is the saturation heat flux for the triple junction solar cell?
Excellent question. You can probably go up to about 2,000, maybe a little higher.
That's about like 3 sums.
Hmm?
That's about 3 sums. 2,000. What does it mean?
2,000. So what are you trying to figure out? The angle? Sorry.
Is it 2,000 sums? Like
2,000 suns on the cell. Yeah. After that, the diode layers are separated by tunnel junctions, and after that, the tunnel junctions break through. Yes, sir.
Just to be clear, the benefit of the higher acceptance angle, say going from 1 degree to 3 or 5 even, is the benefit in terms of the system cost that you can do cheaper tracking? Or?
Yes. I mean, the benefit is that current trackers don't work sub-degree. They just don't work. So the benefit is it doesn't work at all. Now, maybe in the future, somebody will find a tracker that be able to make the trackers more accurate, but surely it'll come with a cost.
What's sort of the angle right now for tracking technology?
Oh, a couple of degrees. Yeah. All right. So the next part is thermal. Solar thermal. And again, the reason for doing direct conversion of solar to heat is because the way we produce heat nowadays is getting expensive and also produces CO2, right? So it'd be nice to be able not to burn natural gas. Okay. So here's stuff in the past where this technology has been used. Let's see, that's a fire station in Chicago, that's a residence in Chicago, that's in Portugal, that's in Albuquerque. So this technology has been used, but not with the conditions that we want. Okay? So this is non-tracking technology, it's low concentration. Where's my, can't see it. Let me change pointers. Way better. So these are non-tracking, but the current non-tracking technology is low temperature. And we want high temperature systems. Okay? Now this is what you can do. Okay? If you take a flat plate collector, which is the most common thing, you cannot boil water. But if you take, this is a code name for the non-imaging optics stuff, you can get very high temperatures, 200 C, with reasonable efficiency. So this is the reason why we developed this. Okay, big gap. So we can replace electricity and natural gas, and I think the most promising application is cooling of buildings. I mean, if I look around the Valley of California, it gets really hot in the summer, and all the roofs have all that solar, and that solar should be used to cool the building and not heat the building. So that's a very nice application. The sun's available when the cooling is needed, more or less. There's also an industrial aspect to it, agricultural and commercial. So lots and lots of reason to generate heat from the sun if you can do it practically and at low cost. So, why is this repeating? Yeah, I don't know if this is all that marvelous, but we think the work we're doing will pay back against natural gas in 3 years. So for the venture capitalists here, that's not a bad rate of return. Yes, sir.
Does that include installation costs?
Yeah, well, okay. Yes, actually, yes, because the The goal is something like $90 a square meter, and we think we can, plus including installation. We think we can beat that. We think we can beat that. Pretty sure we can beat that. The goal we've actually set to our sponsors is $150 a square meter, and we expect to beat that. And we think this is probably okay, probably correct. Okay, how is it done? So it's done with nonimaging optics. It's done with strings. It's done with vacuum receivers and nonimaging mirrors, which look like that. And I think what I need to do now is show you a fast movie. I can do that. So this will kind of show you how the whole year is contained by the optics, if we get this to go. No. I don't want updates. I want to show this. Okay, so if I hit this, it'll vary the input angle, and it always reaches the absorber. Okay, so that's how these string designs work. Okay, always reaches the absorber. So that's how these thermal designs work. Okay, I'll send it back. So there's no tracking here. There's no adjustment. These are fixed to the roof or fixed to the ground. Okay. All right. Go back. Questions? Do you see any questions on what you're seeing? No. Okay. In that case.
How much the light then or energy bounces off of the collector?
Yes. You mean for no reflections? Is that what you mean?
Well, no, down there.
Well, there's a piece of glass. You have to get through the glass. That's probably 8% for two surfaces. And then you have to get absorbed. The absorptivity of these things is in the mid to high 90s. So it's pretty good. It's pretty good. Okay. Oops. No. I don't want to buy it. I just want to close it. Good. So now I got to bring up the rest of the PowerPoint. Okay, so we were here. We're here. Okay, so that's how these work. The vacuum tubes come from China, and I brought a sample with me. So that's in a city which is south of Beijing and north of Shanghai. I brought a sample with me, so you can see how beautiful they are. But it's all glass. I think I'll just, those of you who are interested can just come up after. I'll show it right now. And if you're interested, I'll just come up and look at it. But because if we were to drop it, it would be a shame. So that's what these look like. They're glass. They have a vacuum inside. They have a dark coating. And in real life, these are about 1.5 meters. And very inexpensive. The full 1.5 meter tube is under $3, which is just amazing. That's how we get our low costs, because each tube is worth about a third of a square meter. So if a third of a square meter is $3, a square meter is $10. So that's very attractive. Okay. Questions on this before I turn to the last subject, which is kind of fun. It's a student project, and yes, sir.
Would this work with a circular aperture where it was concentrated in both dimensions?
Well, then you wouldn't be able to be non-tracking. because you need to take, I mean, the whole day is a huge angle. Yeah. Yes, sir.
For some of the applications with things like industrial processes,
Yeah, yeah.
is that, what would need to be in place for those applications to actually be a reality?
That's actually a good question. So we're starting a collaboration with UC Berkeley to drive a organic Rankine cycle engine. That's one application. And it's, Zach, are you in the room? There he is. Okay. Zach is the student and Dan Kamen is the professor. Okay. So there are applications, they're exciting, and they require these high temperatures. What other questions? No. Okay, so the last little bit is a student project I have, which in engineering is called service learning, and it's very popular. How to bring daylight into a building. Like, wouldn't it be wonderful if this building has some daylight, right? Maybe not right now, but generally, okay? More comfortable and all that. So the idea is to bring the concentrated daylight through a liquid light pipe. Liquid light pipes are a new technology, inexpensive, very efficient. So our first job is to light up the exhibits of the California Mineral Museum in Mariposa. So here's a typical group of students. We work with UC Davis on this, a typical group of students, and a concentrator on the roof of the building, and here's what it looks like when it comes out. Right? Nice daylight, sunlight. And here's what happens when you display some minerals with it, so they look rather pretty. And lots of benefits. No heat, it's cold light. It's more attractive to people like daylight, more attractive. And the museum is building a new building, so we're looking forward to having this building illuminated with our technology. That, I think, is all the projects. So if you want to, come on up if you want to see what these tubes, they're lovely. If you want to see what these tubes look like, come on up.
So if you have any other questions, ask them now. And if you need to go to your next class, that's fine. Did anyone else have any questions for Dr. Winston that he hasn't addressed already? Okay. Well, thank you, sir.
Thank you.